previous class I introduced something called net present value and cash flow, and I also gave an example how to make use of this particular concept in making a decision. It was related to a filter and a centrifuge. You can use a filter for removing the solid, or you can use a centrifuge for removing the solid. Centrifuge of course is very advantageous because it retains less amount of liquid, whereas filter will retain more amount of liquid. So if liquid is your desired product, then if you use a filter you lose 800 kg of the liquid, and if you use a centrifuge you lose 160 kg of the liquid. So profit every year because of filter will be 7.2 lakhs, and profit every year because of the centrifuge will be 7.84 lakhs, because you get more liquid when you use a centrifuge, so you make more profit because liquid is your final product. So I showed you the same table last class. If you are purchasing a filter it is 1 lakh, and if you are purchasing a centrifuge it is 1.5 lakh. We put a negative term here because we are spending when we purchase the item, and we will put a positive term if it is a profit or if the cash is coming to us. It will be a negative if the cash is going away from us. Now you have the annual maintenance contract. The filter will be 50,000 rupees every year and the centrifuge will be 80,000 rupees every year. That means we have to spend more in maintaining the centrifuge every year. So what happens if you look at the net present value for each of these 50,000, that means 50,000 divided by 1.1, where this 0.1 comes because of the money value, and this one the second years will be 50,000 divided by 1.1 raised to the power 2, and third year will be 50,000 divided by 1.1 raised to the power 3, and fourth year will be 50,000 divided by 1.1 raised to the power 4. So if you add up all these you will end up with this particular number, understand. So it is not exactly 50,000 into 4, 50,000 into 4 will be 2 lakhs, but actually the net present value for the AMC is only 1.58493, understand. So that comes because the value of the money which you have in the first year is much less than the value of the money you have it today. Now if you look at the centrifuge, same thing, your AMC is 80,000 every year, and if you calculate the net present value by dividing this 80,000 by 1.1, this 80,000 by 1.1 square, this 80,000 by 1.1 cube, and this 80,000 divided by 1.1 raised to the power, and if you add up all of them you will end up with 2,53,589. So it is not exactly 3,20,000, if you actually multiply you will get that. Now the profit for filter, as I showed in the previous slide, every year you will get a 7.2 lakhs profit, and because of the centrifuge every year you will get 7.84 lakhs. But when again you calculate the net present value, the cash flow, then these are the numbers you get. So you take all the positives and you take all the negatives together and subtract. So if you have a filter you are going to have this much amount of profit, okay, that means 20 lakhs 23,810. If you have a centrifuge, the amount of profit you are going to make is 20 lakhs 81,585. So of course centrifuge is better than the filter, because total amount of profit in the 4 years, the cash flow, and you subtract the annual maintenance contract and you subtract the purchase price as of today, that is year 0, this is the difference you get. So that means you will make a profit of 57,775 if you have a centrifuge, better than a filter. So it is advantageous to have a centrifuge. So you see that although there are the cost of the centrifuge is more, the AMC is more, you are going to get more profit every year because of the centrifuge, and if you bring down all of them and today's value, then you end up with a advantage for the centrifuge in the order of 57,775. I got a Excel of the same thing. Now this is the Excel sheet of this same problem. So same table, filter, this is the cost of the filter, cost of the centrifuge, then the AMC for the filter, AMC for the centrifuge, profit for the filter, profit for the centrifuge. So total discounted cash flow for the filter you get 20 lakhs 23,810, and for the centrifuge you have 20 lakhs 81,585. The difference for the centrifuge is 57,775. that is for a discount factor of 10%, that means 0.1. So the advantage of doing a Excel is we can change this number. If the discount factor is 5%, that means difference between this current year and the next year, the difference is only 5%, unlike the 10% which I have it here. So if I put in that 5% and have a look at this number, so if I put in an 5%, you see the difference comes out to be almost 70,562. So depending upon the discount factor, the advantage between the filter and centrifuge changes, understand. So if the discount factor is less, instead of 10%, if the discount factor is 5%, you see that it is more advantageous to have your centrifuge rather than the filter. So instead of 10%, if I put it as 15%, the discount factor of 15%, then you see the difference between the filter and the centrifuge goes down from 57,000 when it was 10%, it becomes 47,000 if it is 15%. So you see, if the discount factor is larger, that means the value of the money is going down much more, then the difference between the filter and the centrifuge is less, because the amount of money which we get because of the profit from the filter and the centrifuge keeps going down much more, because you are dividing by the that 15% comes in the denominator. So that is why you are having much smaller number. So if instead of 15% as a discount factor, if I take it as 20%, see the number has still come down dramatically. It has come down, the difference between is only 38,000. So if the discount factor is larger, then the difference between the advantage of having a filter and a centrifuge keeps coming down. If the discount factor is much smaller, the difference between the advantage of having a filter and a centrifuge gets enhanced, that means it gets magnified, because as you can see the profit in a centrifuge is much more, 7,84,000 every year, whereas the profit in a filter is 7,20,000. So you have around 60,000 every year having a centrifuge than a filter, and if the discount factor keeps coming down, this difference gets enhanced in today's value. Okay, so depending upon the discount factor, the difference between a profit we make out of a centrifuge and the profit we make out of a filter can vary from a very small number right up to a very large number. Okay, let us go back to our problem. So you see that the efficiency between a centrifuge and a filter is different, the cost of the centrifuge and filter is different, the annual maintenance contract between a centrifuge and a filter is different, the profit you make between a centrifuge and a filter is different. So we make use of all these together in deciding on whether I should buy a centrifuge or whether I should buy a filter. Okay, so when you select an equipment in your downstream, you always face such doubts, you will always face these type of problems. Which equipment should I buy? Filtration, should I buy this or should I buy that? Chilling plant, should I buy this type of chilling plant or should I buy this type of chilling plant? Heater, should I buy this type of heating element or should I buy some other type of heating element? Should I go for a steam or should I go for a hot oil heating? So you always face this type of doubts or this type of worries when you are selecting equipments or when you are selecting your utility strategies. So selection of equipment over another depends on several factors. So this is what this particular slide tells you: performance of the equipment, how good the equipment is, what will be my yield of the product if I use this particular equipment, what will be the purity of my product if I use this equipment. So the performance of the equipment is one of the criteria in selection. For example, if I use a heating element the product may get charred if it is very temperature sensitive. Sometimes you may go for a chilling equipment instead of heating for separating two different fluids. If they are temperature sensitive, then heating may lead to production of polymer or production of charred product. So purity and yield of the product plays a very important role in selection of the equipment. Then comes operating condition. What temperature am I going to operate, what pH am I going to operate, what pressure, do I need very high pressure or can I work at room temperature, do I require very high temperature. If I require very high temperature, I may go for steam, or sometimes I may have to go for hot oil and so on. pH, is it going to be very acidic pH condition or is it going to be neutral pH condition. If it is going to be acidic, then your material of construction has to withstand the acidic condition. If it is a neutral, then you can use very simple material of construction. Mild steel is very cheap and it can withstand normal conditions in pH, but if you are going to have a very acidic pH, you may have to go for some other special type of steel. Then the cost of the material may be very high. Amount of consumable solvents required to operate, how much solvent do I require to operate this particular operation, how much consumable chemicals I will require to operate, I need to consider actually. Do I require too much solvent? If I require too much solvent, then obviously my operating cost goes up, I may have to use the solvent, I may have to recover the solvent, so again the cost is very high. So how much solvents will I require, can I do the operation in this particular downstream vessel with minimum amount of solvent, if so then that is very advantageous for me, isn't it. So how much solvents and consumables I will require, that will decide on how I select the equipment. Material of construction, do I can I operate with a mild steel, do I require stainless steel, do I require glass lined steel, do I require titanium. So each of these material of construction leads to different total cost of the equipment. The cost of the equipment will depend upon the type of material I select. So what material of construction am I going to use, that is one of the important parameter when I am selecting an equipment. Then comes the actual cost of the equipment, annual maintenance contract and other expenses I will be incurring on the equipment. So I should find out, for example if I am buying a BMW, I will spend lot of money on maintaining, right. So that is going to be a continuous expense. If I have a Maruti 800, no problem, the cost I will incur is very little. So not only the original cost of BMW, but maintaining BMW also I need to spend lot of money. So you need to keep that point in mind. Ease of operation, how easy it is to operate, do I require very complicated instrumentation and control if I want to operate, can I operate with the unskilled people or semi skilled manpower, or do I require very complicated highly trained manpower. So ease of operation is very important. Then comes utilities, what are the utilities required, do I require steam, do I require air, do I require nitrogen, what type of gases I require if I want to operate, do I require inert conditions, for example some motors may generate heat, so I may require cooling water for the motors. So I need to keep all those points into mind, that is the utilities requirement, because as I said long time back, it is not just enough to have an equipment. If you want to make the equipment running, you may require lot of support services. Then waste generated, how much waste is it going to generate, so because waste generated is something I have to send it to effluent plant and treat it, I cannot just throw it out in the gutter. So whatever waste I generate, I spend money on treatment. So is this equipment going to produce lot of waste or is this equipment going to produce little amount of waste. So you need to consider both the aspects, depending upon the amount of waste generated by the equipment you may select your final choice of downstream. Seamless fit with the subsequent unit or previous unit, because I showed you many flow sheets where you have one unit operation which goes into another unit operation which goes into another. So when I buy a downstream equipment, how will it fit into the next downstream. So if I am heating a downstream and if the next downstream is cooling, then obviously from the high temperature I need to bring in to the low temperature. So it is not exactly matching with each other. If I am doing an unit operation at a high pressure and the next equipment is at low pressure, I need to bring the pressure down so that I can do it in the next equipment. So that is not very comfortable fit. So that is why it means seamless fit. If the pressures in the subsequent units are similar, if the temperature in the subsequent units are almost similar, not exactly, then I need not spend extra energy to bring down the temperature or change the pressure. That is what it means as seamless fit. So you need to see what are the operating conditions in the next unit, what is the operating conditions in this unit, and together how they fit with each other. That is called seamless fit. So you need to consider so many factors when you are selecting an equipment, and it is not only the performance, that is the performance item 1, but it is several other factors you need to keep in mind before you select a equipment. So you need to keep that point very, very important actually. There is one more cost factor which I forgot to mention, it is called payback period. We talked about the equipment cost, we talked about operating cost, then we talked about net present value, then we talked about cash flow. There is something called payback period. It is how the amount of time I will take to pay back whatever investment I made. For example, if I borrow 1 lakh from you and I pay 50,000 rupees this year and 50,000 rupees next year, I will be paying back your 1 lakh in 2 years, is not it? So because you will be asking how long you will take to pay it back, that is the first question you ask whenever somebody comes to you for loan, how many years you take or how many months you will take. That is what is called payback period, and that is very, very important, because if you go to the bank and take a large loan for setting up a factory, bank would like to know how fast you will pay the money back. It tells you how good the investment is. If the payback period is very small, that means the investment is very, very lucrative. So the banks also will be interested. If you are going to tell the bank that I will take 10 years to pay back, they will not be happy. If you go and tell the bank I will pay the money in 1.5 to 2 years, they will think yes, this project is very good. So they would rather support this project rather than the other project, which will take a very, very long time for payback. So payback period, how do you calculate? If suppose cost of setting up a plant is 1000 crores and every year I make profit in the plant, correct? So imagine I make 50 crore profit after tax. So this amount I pay back to the bank. So 1000 by 50, that comes to 20 years. So the 1000 crores I bought from the bank as a loan, I will paying the bank back in 20 years all the amount, assuming that every year I will make a profit after tax as 50 crores. So the bank will be interested in this particular number, so they will know that you will take 20 years to pay it back. So if there is another project and if that project the payback period is 10 years, bank will think that project is better than this project, so they would rather fund that project rather than this particular project. So that is why payback period is an important number, and it also tells you how long you will take to clear all your debts, because you have borrowed 1000 crores and after 20 years there are no debts for you. So it tells you, or it gives you an idea of how long you will take to clear your debts. So payback period is also an important parameter which tells you the soundness of your investment. It also tells the bank the soundness of the person who is borrowing the money. So when you go for a downstream equipment, and when you talk about designing a downstream equipment, you need to consider several factors. So what does the design means? One important parameter is called the cycle time. Suppose if you are designing a filter, how long the filtration will take place, that is the cycle time. If you are designing a dryer, how long do you require to dry the equipment to reach the moisture content to some value to some other value, that is called cycle time. If you want to heat a material from room temperature to 100 degrees, how long it will take to heat, that is called the cycle time. So if you are doing a heating and cooling, how long you will take to heat the material, how long you will take to cool the material, so together that is called a cycle time. So if you are trying to settle solids in a slurry, how long do you need to keep the liquid stationary so that the solids will settle down, that is called cycle time. So cycle time is a very important parameter you need to design. Next is operating parameters, what will be the temperature, what will be the pH, what will be the pressure, if it is a fermenter like what will be the dissolved oxygen, these are called operating parameters. Next is hardware details, that means the size of the equipment, how much will be the diameter, how much will be the length, all these parameters actually. So hardware we are not going to do any hardware design, we go to vendors and then vendors will suggest certain equipments for us and we can select from them. So you need mechanical engineering expertise if you want to design a hardware, that means the diameter of the vessel, length of the vessel, thickness of the flange, thickness of the vessel, radius of curvature, and so many other parameters which are very mechanical engineering, and we are not going to do any of that. Generally we go to a vendor. Now when you are designing a equipment, there are many issues which you need to consider. One is called the idealization, that means we generally consider whatever we do in a vessel at ideal condition, that means if you are considering a gas and a liquid, we assume that the gas gets mixed completely with the liquid, that is an ideal condition. Generally it will not, but we will consider it as completely mixed. Okay. Suppose if I am saying I am going to heat a liquid of 1000 liter from 30 to 80 degrees, we will assume all the 1000 liter is uniformly getting heated up to 80 degrees. So we do not assume any difference in temperature inside the liquid, so that is an ideal condition, agreed. If we assume we are mixing a solid and a liquid thoroughly so that the solid gets dissolved, we assume that the solid completely gets mixed and dissolves, that is an ideal condition. So generally it becomes easy for us to do a mathematical calculation design using ideal conditions. We will not go into non-ideal conditions because it complicates the design equations, it complicates the equations which we need to solve. So generally we assume ideal conditions. Then type of design equations, are we going to do mass balance type of equation, are we going to do heat balance type of equations, or are we going to go very deep into the equations and calculate the velocity of flow inside a stirred vessel. So what type of designs we are going to perform, so that is the next step. Third step is parameters and data. For example, if I am going to do settling, I need to know the density of the liquid, density of the solid, the viscosity of the liquid, the surface tension, so many parameters I need to know. Same thing, I need to know all about the solid properties, the size of the solid, size distribution of the solid, and so there are a lot of parameters we have to know when we do this type of downstream calculations. For example, if I am doing a distillation separating two liquids, I need to know the vapor pressure data for liquid 1, I need to know the vapor pressure data for liquid 2, I need to know the viscosity of both the liquids, I need to know the surface tension, I need to know the where these two liquids mix, are they miscible or are they not miscible. So all these parameters I need to know. So collecting data is a big challenge for downstream process calculations. Many times we do not find data, many times. So what do we have to do? We sometimes approximate, we sometimes assume, we go to the net, we go to the books and try to locate data. So sometimes we may have to do experiments in the lab to collect data. So if you are very serious about the data, you may have to go to the lab and try to collect data. If you want to know the viscosity of a liquid, you go to the lab and get the viscosity data for the liquid. If I want to know the surface tension, either I assume some value from the net or I actually calculate surface tension. If you want to know viscosity effect as a function of time and temperature, we may have to do the experiments, or you may assume a approximate like linear change between temperature and viscosity. So data is a big challenge, collecting data is a very big challenge, getting it from books, literature, net, collecting your own data. So this is going to be the main bottleneck, and this will take you a long time. Next is conversion factors. As you know, you have FPS units, CGS units, SI units, so many units are there, and when we do some problems also you will come across. So conversion factors, you have to be very thorough in conversion factor, kilocalories, kilojoules, foot, meters, centimeter, liter, meter cube, gallons. So each country has different units, and converting them is going to be a big challenge for you also. So you need to remember all the conversion factors. Next is the design safety margin. When we assume ideal conditions and do a design, you know it is very ideal, it is not real. So we generally add some extra margin, 10%, 15%, 20%. So how much do I add is always an important point you have to keep in mind actually. Should I add 10% extra or should I add 20% extra? If you add 20%, that means you are over designing. If you are over designing a vessel, of course you are going to spend more money buying that vessel, right. So you need to think, do I need to over design the vessel, or 10% looks a very good margin, but then the safety is not very high, the equipment may be not performing as good. So it is a challenge between equipment performance versus extra design, hence extra equipment cost. So you need to select, should we do 5% extra margin or 10% or 15% or 20%. And finally vendors, you should know who are the vendors manufacturing. If I want to buy a centrifuge, I should know who manufactures centrifuge in India or if outside India. If I want to buy a distillation column, I should know who manufactures various distillation columns, various types of distillation columns. If I want to buy a motor for agitation, who are the various vendors. So you need to know the vendors available in India or outside India. Okay. There are some few small rules which are very useful when you are doing design. One is called the 0.6 rule. It is very interesting rule which gives you a ballpark figure of the cost. For example, if cost of the original operation is related to the size of the unit raised to the power 0.6. Generally this number is called the exponent, it varies between 0.5 to 0.7. Do not ask me why you get 0.6, it is based on experience, and this number is of the order of 0.5 to 0.7. So cost of original operation is directly proportional to size of the unit raised per 0.6. So if you have another cost of new operation and the size of unit is 2 times size of unit 1 and size of unit 2. So cost of original operation divided by cost of new operation will be equal to size of unit 1 divided by size of unit 2 raised to the power 0.6. So for example, if I have a 100 liter vessel capacity and I need the cost of operating this vessel is 5,000 rupees. If I have a 200 liter vessel, the cost of operation will not be 2 times 5,000, that means it will not be 10,000 rupees, but it will be much less than 10,000 based on this formula. So original operation is 5,000, original vessel size is 100, new vessel size is 200. So cost of new operation, so I can calculate like this, 5,000 into 2 raised to the power 0.6, 2 comes because of 200 by 100. So it comes to 7,578. So what it tells you is, if I have to operate a vessel of 100 liter capacity and it costs me 5,000 rupees, and if I want to operate similar vessel, just the size is 200 liter, the cost will not be 10,000 rupees, but it will be 2 raised to the power 0.6 extra rupees. So it is 7,578 rupees. So it is not 10,000 but less than 10,000, but it comes out to be 7,578. So this 0.6 rule is very useful. Sometimes depending upon the type of equipment, then this exponent may change. If it is a very complicated equipment, it may go to 0.7, if it is not so complicated, it may become 0.5. So all it says is, you cannot, just because the vessel size has moved from 100 liter to 200 liter, you cannot just multiply by 2 5,000 and tell it is called 10,000 rupees, it will be less than that. Same 0.6 rule can be also used for getting a price of an equipment. This rule again tells you cost of equipment 1, size of equipment 1, cost of equipment 2, size of equipment 2, this raised to the power 0.6. Okay. So if a cost of a 100 liter vessel is about say 5 lakh rupees, a cost of 200 liter vessel will not be 10 lakh rupees, please remember, but it is 2 raised to the power 0.6 approximately. So it will be around 7.57 lakhs rupees. So this exponent can vary between 0.5 and 0.7. So if it is 0.5 it will be much less, right. So it is not exactly 2 times 5 lakh which is 10 lakh rupees, but it is much less, and this exponent depends upon the how complicated the equipment is. The equipment is very complicated, it will be 2 raised to the power 0.7. If the equipment is not least complicated, it can be 2 raised to the power 0.5. So it will be in between. So equipment of 100 liter capacity, if it is 5 lakhs, equipment of 200 liter capacity will be 2 raised to the power 0.6 into 5 lakhs. That is what this 0.6 rule tells. It just gives you a ballpark figure. If you want to know the exact price, you have to go to the vendor who is manufacturing the equipment and go and ask him, I want to buy a 200 liter vessel, what is the cost, I want to buy a 100 liter vessel, what is the cost. So the final price, if you want to get exact calculations done, you go to him, but you can use this type of formula if you are doing it in your lab, in your office, just to get a ballpark figure of the cost. There are 2 types of products which are manufactured in bioprocess engineering. One is called the low value high volume product, that means the selling price is low but you make large amount of product. Other one is called high value low volume product, that means selling price is very high but you make only little amount of product. So this low value high volume product like ethanol, you make large quantities of ethanol but the cost of ethanol is cheap. Same thing, nowadays many antibiotics are made in large volume, cost is very cheap. All this penicillin and different types of penicillins, it is all made in large volume. Suppose you look at some pharmaceutical product like insulin, statins. Statin is a cholesterol lowering compound. You might not make such a big quantity but the price is very large. So you may make only 10,000 kg but each gram may be costing about 10,000 rupees, whereas you make metric tons of ethanol but cost of ethanol will be only few rupees. So you see the difference. So that is why one is called the low value high volume product, other one is called the high value low volume product. So if you look at low value high volume product, the goal of a downstream and the goal of a fermentation is very different. You all the time want to make large quantity of material, so maximize product yield in the fermenter, in the recovery as much as you can get, because you want to sell as much, the profit is very little. Use known hardware, do not go for new hardware. If you use known hardware, always you go to the vendor and it is cheap. If you want a very special hardware, then the vendor has to make it specialized, so equipment is expensive. Standard size, right. So if you have a standard shoe size, you go to a shop, then it will be cheap, whereas if you want a very specialized cut for your foot, then cost of that shoe is very high. Try to reduce operating cost, that means all the time keep seeing, can I reduce the cost of the steam, can I use less steam, can I use less utilities, can I use less raw materials, because every time I need to improve on the profit because the value is very low. Improve strain, so you can do microbiology and see whether the strain can be, tolerance can be improved. That is how new ethanol tolerant strains have been discovered over the past few years. Reduce overhead cost, because the value is very low, you are selling the product at a very low price, so obviously do not have too much of overheads, keep your overheads very low. See whether you can convert batch process into continuous process, because if you can do continuously, then you will be continuously manufacturing the product at the same purity and yield without disturbing any of the equipments. That is why continuous process is very ideal for high volume or high quantity material. standardize, keep everything standard, do not try non-standard. As I said, if you have a special shoe made for yourself, it is very expensive. If you use this shoe, go to Bata and buy a shoe, it is cheaper. Economy of scale, you have a very large plant, and when you have a very large plant, the overall cost will be also low. So, very large plants, that is why high volume products will always be manufactured in very big factories, not in small factories. So, these are some of the approaches by which you can handle low value high volume product. Okay. On the contrary, if you look at high value low volume product, because here you are making only small amounts, but the cost of each kilogram or each gram is so high. So, you need to recover all the product, because each gram you lose in the effluent, you are losing profit, you are losing money, because it is a high value, each gram may be costing thousands of rupees. So, your product recovery and isolation should be fantastic, the efficiency should be almost 100%, you do not lose any of your product in the waste. Purity is very important. If you look at all these drug or pharmaceutical products, purity is a very important competition. Another very important point you need to remember is, you will not be able to have the high value low volume product forever and ever. If tomorrow another manufacturer comes and they start a company, they become your competitor, then the product cost, selling price comes down. Okay. So, you have to always keep in mind, there is no monopoly for a very long time. This year I will have a monopoly, next year I may have a monopoly, but third year somebody else may be manufacturing that product, then you have to cut down on the cost. So, what happens, your high value low volume product will slowly end up like a low value high volume product. You have to keep reducing the selling price of the product. That is why, for example, you know, mobile phones were so expensive once upon a time, nobody could afford it about 7-8 years back, but now practically it is throwaway price, because you have many competitors manufacturing mobile phones. So, obviously it has become almost like a high volume low value product, but about 10 years back it was like a high value low volume product. That is happening to everything, not only mobile phones, even the service. Some of the services may be very expensive 10 years back, but today same services are so cheap. So, the type of strategy you employ depends upon the value of the product, depends upon the volume of manufacture. If the volume is very large, you adopt some strategies. If the volume is very small, you adopt some other strategies. If the selling price of the item is very large, you adopt some strategies. If the selling price is very less, that means your profit margin is also very less, you adopt some other strategies. So, depending upon the volume you manufacture, depending upon the price of the item, you employ different strategies. So, when you use a fermenter or when you use a bioreactor, you get metabolites are small molecules, or you get biomolecules, and the type of strategy of separation depending upon the type of molecule you get. So, you need to know some differences between the biomolecule and the metabolite. So, what is a biomolecule? It could be a DNA, it could be a protein, it could be amino acid, enzyme. Enzymes have very large molecular weight, proteins have very large molecular weight. If it is a metabolite, it is going to be a small molecule, it could be organic acids, alcohols, ketones, aldehydes, even vitamins, they are all metabolites. That means these are produced during the fermentation process or during the biotransformation process. So, biomolecules are generally sensitive to environmental conditions. Environmental means pH, temperature, and the presence of impurities, presence of other toxins. So, you need to be very careful when you are doing a separation or when you are mixing a solvent, whether the biomolecule is tolerant to the solvent. Can I add a butanol to an enzyme? Butanol may be toxic to the enzyme. So, a biomolecule is always sensitive to environmental conditions. Shelf life, that means can I store these biomolecule for a long period of time, 3 months or 6 months, how stable it is going to be. So, that is very important. That is why you need to add stabilizers after you purify a biomolecule. Stabilizers could be antioxidants or antiozonants and so on actually, and generally biomolecules have large molecular weight, whereas if you look at a metabolite, generally they are much smaller molecular weight. They will not be very generally they are not very sensitive to environmental conditions. So, you do not have to worry about shelf life also. You may be able to store alcohols for a very long time, you may be able to store many of the small molecules for a very long time. You do not have to worry about toxicity or presence of other impurities which may reduce their activity. Separation, generally for metabolites we can use distillation columns because they are not temperature sensitive, whereas a biomolecule will have problem using when you resort to a distillation column. So, what do? We generally use extraction. So, in many biomolecule downstream you will use an extractor. Once the extraction is done, once the biomolecule is removed, then the solvent can be distilled for recovery and then sent back to the original extractor. But when the enzyme or when the biomolecule is present, you will not resort to a distillation, whereas if you have just a metabolite recovery, you resort to distillation. For example, if you take fermentation of sugar to alcohol, the very first step is filtration, that is followed by distillation to remove the alcohol, whereas if you have an enzyme after fermentation, you will do filtration and you will not do a distillation. What will you do? You will do an extraction, understand, you will not do a distillation because the enzyme present in the fermentation broth can get deactivated. So, what do? You do an extraction and the enzyme is taken up in the extractor, and then you separate the enzyme from the solvent using some salting out, okay, and then you take the empty solvent and do a distillation when the enzyme has been removed. So, understand. So, a fermentation of sugar to alcohol, you can resort to distillation because ethanol is very stable at high temperature, whereas if you have an enzyme in your fermentation broth, what do? You cannot do distillation, you have to resort to extraction. So, you see the difference depending upon the type of downstream which you want to do, you need to change the unit. Okay, there are many downstream operations that are possible and we are going to talk about it in the next 30 or 35 lectures, and each one is based on a physical or chemical principle. Irrespective of the downstream, there is always a physical or a chemical principle on which it is based on. For example, if you take filtration or a screening or membrane, it is generally based on particle size. That means a filter unit will separate particles of certain diameter and it will let particles of certain other diameter. So, it is based on the size of the particle. Same thing with sedimentation. What sedimentation? We are trying to settle large solids in a slurry. So, again it is based on particle size, agreed. So, if you have large particles and the liquid is stationary, so the large particles will settle down and the very small fine particles may not settle down, but the large particles will settle down, and this settling is called the settling velocity, and there is something called terminal settling velocity, and this terminal settling velocity depends upon the difference in densities between the liquid and the solid, and it depends on the viscosity of the liquid and depends on the particle size of the liquid. Okay. So, again particle size comes into the picture. So, sedimentation is also based on particle size. Now, let us look at something called gel permeation chromatography. So, this depends upon the molecular weight of the various components present. So, larger molecular weights get separated from smaller molecular weight, larger sizes get separated from smaller sizes. So, gel permeation chromatography is based on this concept. Let us look at centrifugation or cyclone separation, that is based on density. The density difference drives the operation. If you look at again denaturation or precipitation, so you have something called the temperature. If you are looking at crystallization, again temperature plays a very important role, and solubility of the material. So, when you are crystallizing, the least soluble material will crystallize out and the most soluble material will be retained. So, the solubility plays a very important role in crystallization. If you look at liquid extraction, that is I am using a solvent to extract a liquid or a solid, the principle is based on partition coefficient. The solute gets partitioned between the solvent and the solution. So, if it has got a higher partition coefficient, more of the solute will go into the solvent, and if it has got lesser partition coefficient, less of the solute will go into the solvent. So, more of the solute will remain in the broth. So, that concept is called the partition coefficient. If you are looking at adsorption, adsorption is attachment of some material on some surfaces, some solid surface. So, that is it is a surface phenomenon. If you look at distillation, it depends upon the boiling point difference between two liquids or vapor pressure difference between two liquids. So, a liquid which has got higher vapor pressure, that means lower boiling point, will move up of the distillation column, and the liquid which has got lower vapor pressure or higher boiling point will remain at the bottom of the distillation column. So, the separation is based on the vapor pressure. Then comes drying. Drying is nothing but evaporation of a vapor. Vapor could be water or any solvent. Lyophilization, this is called sublimation. So, it is based on the sublimation, because a solid directly goes into vapor, that means solid ice will directly go into water vapor, right. So, that is concept of sublimation. So, you see many of the unit operations on this side has or is based on a physico-chemical principle. Let us continue some more. Dialysis, there is a membrane ion interaction, there is a membrane and ions are interacting with that. So, the ions get separated. Dialysis is very good for separating salts from a solution. Then we have electrodialysis, where you are using an electric force. So, the separation is not only a membrane and a interaction, but there is also a electric force applied, so that positive charged material will go to the cathode and a negative charged material will go to the anode. Then we have something called affinity chromatography. Here it is based on a ligand and an enzyme, or a ligand and a protein. So, there is an affinity between the ligand and a protein, or ligand and an enzyme. Then we have something called reverse phase chromatography. It is based on hydrophobic interactions. Then we have ion exchange chromatography, it is based on ionic forces. Then we have reverse osmotic membrane, it is based on osmotic pressure. Then we have pervaporation, it is based on membrane and molecule interaction. So, here you see many membrane processes are there, starting from dialysis, electrodialysis, chromatography, then we have pervaporation, osmotic membrane. These are chromatographies and these are membrane based processes. So, we have interaction between the ions, interaction between the ligands, which gives you the physico-chemical principle of separation. There are a lot of analytical tools used in downstream processing. I am just giving you an overview of them. We will talk about it at the end of the course. We need many analytical tools for identifying what type of metabolites or biomolecules present in my mixture and what is the concentration of them. So, when I do a purification, I can see whether it is getting purified, and the most important one is called the chromatography, HPLC. You might have all heard about HPLC. It is called the high performance liquid chromatography or high pressure liquid chromatography. So, it is a solution phase technique. So, what happens is there is a solvent flowing through and there is a stationary phase, and the solution containing a mixture of solutes or mixture of proteins get separated because they interact with the solid material and they come out in a separated form. So, we can use it for identifying, we can use it for quantifying compounds from a mixture. There is something called preparative HPLC. So, I can use it for not only separating, but I can use it for isolating also. If I isolate a protein from a mixture of protein, then I can use that isolated protein for other analytical jobs. That is why we use something called preparative HPLC. Then there is something called thin layer chromatography, that is the TLC. This is a very simple technique using silica plate. We can again look at mixture of metabolites or mixtures of protein using this, and it can be very good for separating molecules from mixture. So, chromatography in various forms are very important for analysis in downstream, both for identification and quantification of compounds. Then we have something called mass spectrometer. Mass spectrometer gives you the molecular mass. There are different types of mass spectrometer. There is something called a MALDI mass spectrometer, then we have the gas chromatograph mass spectrometer, that is GCMS, then we have liquid chromatograph mass spectrometer, that is LCMS, then we have ESI mass spectrometer, electron spray ionization mass spectrometer. So, there are large number of mass spectrometry units available or mass spectrometers available, each gives you the mass of the compound, small molecule or large molecule. Then we have gel electrophoresis for separating proteins from mixtures. So, you have an electric field and you have charged proteins. So, the proteins get separated based on its charge, based on the size or based on the molecular weight. So, it is very good technique for separating out proteins from mixture. Then we have something called SDS page. SDS means sodium dodecyl sulfate, it is a surfactant, sodium dodecyl, it is a sodium salt of dodecyl sulfate, polyacrylamide gel. So, polyacrylamide gel electrophoresis. So, sodium dodecyl sulfate polyacrylamide gel electrophoresis. This is good for separating proteins from a mixture and getting reasonably good molecular weight. We can use a marker molecular weight and then we can tell what is the molecular weight of various components present in my protein mixture. So, it is a very good technique, and you go to any biochemistry lab, you will find a SDS page unit there. So, SDS page is a very important instrumental technique in downstream operations. Then we have gas chromatography. This is good for separating small molecules in a mixture. That means when I have a mixture of small molecules which can be easily vaporized, I can separate the mixture and I can find out what those components are, I can get what is the composition of this component. So, that is a very useful instrument for small molecules. It is not good for proteins. If I have a protein mixture, I need to use HPLC, high pressure or high performance liquid chromatography, please remember that. Okay. So, these are some standard instruments which you will find in any downstream lab, and without that you cannot do any downstream processing laboratory or downstream processing manufacturing at all, for measuring the quantity of proteins, for identifying quantity of proteins and identifying various metabolites. Metabolites means small molecules, and quantifying the metabolites that are present in your mixture of metabolites that comes out from a fermentation broth. So far we have been covering the concept of downstream. So, I talked quite a lot about introduction, issues in downstream, and I showed you some examples of flow sheet and what will a flow sheet contain, what are the various units a flow sheet will contain. I also talked about mass balance, what is the importance of mass balance, how do you use mass balance, and how do you use heat balance, what are the important parameters in this balance. Then I also talked about cost, the importance of costing, how do you select equipments based on costing, and then what are the various principles in different downstream steps. So all these we talked about, and in the next course of time we are going to now get into serious downstream processing equipments or units, things like cell disruption, pre-treatment strategies, solid liquid separations like filtration, centrifugation, and then membrane based processes, adsorption, liquid extraction, membrane separations, precipitations, chromatography, crystallization, distillation, and then we will talk about drying, lyophilization, stabilization of bioproducts, and then finally we will look at utilities also, because without utilities a downstream manufacturing unit has no meaning. Utilities like air, water, steam, hot oil, chilling water, and so on. So if we talk about all these and if we understand how each equipment works, I think we will have a fairly good idea about what are the various components in a downstream processing, how do you go about designing a downstream processing. Okay.